There was a time, let's say 20 to maybe 30 billion years ago, when the universe, as we know it today, did not exist. In fact, at that time itself did not exist in the same way that we experienced it. There was nothing. But try and imagine nothing, it's nearly impossible. The first thing that might come to your mind is darkness. But even darkness is something, it's darkness. Okay, maybe space is something. Because it's empty doesn't mean it's nothing. Our minds are wired to understand and experience the world through objects that exist in space and time. But what if we rewind time to a point where the universe as we know it today did not exist? What was there before the concept of nothingness is shrouded in paradox. It's an absence that can only be defined in the presence of something. Even in the vast emptiness of space, there is always something present making. It is hard to imagine a state of pure nothingness. When scientists discuss nothingness, there is often disagreement about what it means. The definition of nothingness varies, depending on the context and language used. However, scientists have tried to explore this concept and have come up with different theories and equations to understand how the universe came into being from nothingness. Keep watching to find out more. Does nothing exist? East-Western philosophers to consider. Nothing was Parmenides, who argued that nothing can exist. He believed that to speak of a thing it must exist, and since we can speak of things in the past, they must still exist. In some sense now from this, he concluded that there is no such thing as change, and that nothing can come into being, pass out of being, or not be. While Parmenides' reasoning on nothing was largely agreed by other philosophers, such as Socrates and Plato-Aristotle, differ in his conception of nothing. He believed that while these opinions may follow logically in a dialectical discussion, it would be next to madness to believe them when considering the facts. Fast forward to modern times, and Albert Einstein's concept of space-time has led many scientists, including himself, to adopt a similar position to parasites. Einstein believed that the distinction between past, present, and future is only a stubbornly persistent illusion, and that time is relative. Music. Different physicists see different things as nothing, from nothing as a classical vacuum to the idea of nothing as undifferentiated potential. Even if you could remove all the particles in a box and shield it against all electric and magnetic fields, your box would still contain gravity, because gravity can never be shielded or canceled out. Gravity doesn't go away, and it's always attractive, so you can't do anything to block it. According to Newton's physics, it's because gravity is a force, but in general relativity, space and time are gravity. Okay, let's imagine we could remove gravity and every other thing from the system. You'd be left with a true vacuum. Even at its lowest energy level, there are fluctuations in the quantum vacuum of the universe. There are quantum particles popping into and out of existence throughout the universe. There's nothing, then pop something, and then the particles collide, and you're left with nothing again. And so even if you could remove everything from the universe, you'd still be left with these quantum fluctuations embedded in spacetime. You see why it's difficult to just conclude that nothing exists. It's probably better to think of nothing as the absence of even space and time, rather than space and time without anything in them. The laws of quantum mechanics are confusing, predicting that particles are also waves and that cats are simultaneously alive and dead. However, one of the most confusing of all quantum principles are called the Heisenberg uncertainty principle, which is commonly explained as saying that you cannot simultaneously perfectly measure the location and movement of a subatomic particle. While that is a good representation of the principle, also says that you cannot measure the energy of anything perfectly, and that the shorter the time you measure, the worse your measurement is taken to the extreme. If you try to make a measurement in near zero time, your measurement will be infinitely imprecise. This means that there is always a minimum level of uncertainty in the universe, even in space. But what does this mean for the question of whether or not anything exists? It means that even if we were to completely remove all matter energy and other physical properties from the particular region of space, there would still be some level of uncertainty present. This uncertainty arises from the quantum fluctuations that occur in space as particles and antiparticles spontaneously pop into and out of existence. The only pillars of modern physics are Einstein's general relativity and quantum theory. The Wheeler-DeWitt equation is an attempt to combine these two theories. Quantum mechanics deals with the behavior of matter and energy at the smallest scales, while general relativity describes the behavior of gravity at the larger scales. The problem is that these two theories seem to be incompatible with each other. For example, general relativity predicts the existence of black holes, which are regions of space where the field is so strong that not even light can escape. However, quantum mechanics predicts that information cannot be destroyed, which creates a paradox because the information that falls into a black hole seems to be lost forever. The Wheeler-DeWitt equation attempts to solve this problem by describing the universe as a wave function. The wave function describes the probability of finding the universe in a particular state at a particular time. The equation removes time from the equation, treating the universe as a timeless entity. Despite its importance, the Wheeler-DeWitt equation is not a complete theory of everything. It only describes the universe as a static entity and cannot explain how the universe evolves over time. Moreover, it is not clear how to interpret the wave function of the universe or how to test it experimentally. The uncertainty principle, which is a fundamental principle of quantum mechanics, also play a role in the Wheeler-DeWitt equation, which we have talked about before. However, it states that it is impossible to know both the position and momentum of a particle with absolute precision. This means that there is always a degree of uncertainty in our measurements. The Wheeler-DeWitt equation incorporates this uncertainty in its description of the universe, which helps to account for the unpredictable behavior of matter and the energy at the smallest scales. Another candidate is string theory, which views the basic building blocks of reality as tiny strings of mass energy vibrating in 10-dimensional spacetime. If we can obtain a theory of everything, will we be able to answer the ultimate questions: what is space? What is time? What is the universe? Where did it come from? And how it began from nothing? Maybe space is like a phoenix in the eternal cycle of life and death. Maybe time repeats itself in an infinite recurrence of the universe after universe. Or perhaps this is the only universe, after all, with a small hot beginning and a cold dark final. Until the day comes when we discover how to extract more information from the universe than presently seems possible. We have no choice but to face our ignorance. The Big Bang still happened a very long time ago, but it wasn't the beginning. We weren't supposed to be. Some even go as far as to say that the universe is not real. Everything we see, touch, or experience is just a story being created by our brain.